Hello, ladies and gentlemen, and welcome back to our very last question on the 2007 Euclid Math Contest. It's question number 10. Once again, I'd like to take this time to encourage you to try this question, even if it's just part A, if you haven't already given it a try. Okay? So let's take a look here at question 10. As I say, there is an A part. There's also a B part. We have to write full solutions for this particular question. So let's get cracking. Question A, in the diagram, the circle is tangent to xy at y and xz at z. So we've got our points of tangency here. And point T is chosen on the minor arc, so this arc down here, yz, and a tangent to the circle is drawn at T. So T is chosen. Do we know how T is chosen? But once it's chosen, we draw the tangent, and it's going to be a unique tangent, and they call it VW. Prove that the perimeter, so it doesn't look like they're giving us any more information on where T is chosen. T seems arbitrary. Prove that the perimeter of triangle VXW is independent of the position of T. Okay, so that's why they didn't give us more information about T. T can move, so, So the perimeter of this triangle doesn't matter where T is. So that's interesting. We want to show that the perimeter is always the same. Okay. So with a question like this, T is variable. And I don't mean like T is variable as in it represents a value. I mean, T can vary where it is. And once we vary T, that means that the tangent line will change sort of its direction and probably its length depending on what angle it's coming in at. So VW isn't fixed. The positions V and W aren't fixed either. And yet, despite all this change, we should still get the same perimeter. So, let's draw a couple examples and see how weird this can get. So this is just me exploring the question a little bit. So I have my circle, and we'll say it comes through here. I don't really need the rest of the circle over here. As far as I know, I might need more of the circle, but as far as I know, this should be fine. So we pick a point T here, and we get a nice clean tangent, and that should have the same perimeter. There's your V, your X, and your W. And that should have the same perimeter as, so we still have we have the same X, Y, and X, Z, the same rays coming from the same point X. But now if we put T, say, way up here, which is perfectly fine to do, we get a tangent that cuts, and it's a completely different looking type of triangle. But we still get a V and a W and an X, and what they're saying is that these blue lines, these perimeters here for these blue triangles, are the same. So that's interesting. So, I suspect when we're doing something like this and we're trying to show that something is fixed, something is constant, something is independent of our choice of blah, while we might be able to actually calculate the exact value of this perimeter, in order to do something like that, which, that would be sort of the highest achievement is, yes, this perimeter, no matter what it is always, this, 2 times sine the angle at x or something like that. It's a good idea with a question like this to focus not necessarily on what is changing. T, V, W, these things change. They all depend on our choice of T. But focus on the things that stay the same. So what stays the same? Well, X stays the same. Our circle stays the same. We don't do anything to the circle. We come into the question and they say, here's X, and it's got these 2 rays, and they're tangent to the circle. And then we get the choice. Then T is somewhere on here, and as soon as we make that choice T, then a bunch of things start to change. So my suspicion is the value of the perimeter, if we can get it, and there's no guarantee that we can get it, if we can get the value of the perimeter, it should depend simply on things like x, possibly the angle at x, because that's fixed when we start the question. It might depend on the radius of the circle, or the distance from x to the circle, or the distance xy or xz or something like that. And actually, xy and xz would have to be the same length. We'll get into that if that's useful. But when I'm trying to show that something is overall doesn't change or is constant, I try and focus on parts of the question that are set up that won't change. Okay? Now, there might be other things in the question that don't change that I'm not immediately aware of. For example, something that might... actually, something that I just realized doesn't ever change. The sum of these two angles here is always just 180 minus the angle at x, which, as I mentioned, it doesn't change. So that might be something useful. Okay, that might be something important that we can work with. Now, this isn't guaranteed to be the way to do it. You don't necessarily do a question like this by showing, the perimeter must be some value. Other things you can do is say, to solve a question like this, is to say, let t be, I don't know, the one right in the middle, and we get this value. And whatever this is, suppose t were at a slightly different location. Maybe call it t prime. Okay, our perimeter is going to increase by a bit here, decrease by a bit here, and, the tangent line is probably going to get a little longer too. So another way to do that is to make some fixed value by picking some arbitrary t and showing that other t's, well, the differences sort of cancel each other out. So that's another way to do it. And in that case, I wouldn't have any idea what the total perimeter is, but I would show that all of them are the same. So there's sort of two strategies that we could employ. That one, or show maybe that there's some constant value that they all add up to, that all the perimeters are equal to. Now, xy is equal to xz, and this question has tangents and circles. It would be a good idea if we tried to recall some of our circle properties. So what we have here is we have a point x, and we are given a circle, and that is basically the setup for the question. And once you have this point x, they say draw the tangent lines. That's essentially what's going on here. And then from there, you pick your point t. But let's just analyze this for a moment. X and y and x and z, these are going to be the same. I already used blue for the perimeter. So x, y, and x, z, these are going to be the same value here. If you haven't seen this before, that's okay. Tangents, when connected up to the origin, which we might call O here, form right angles. And it's the same radius, r. And OX is the same hypotenuse for both, so you're going to get the same length for both x, y, and x, z. Now, the question is, can we use this fact, or, do we have to invent this r? Maybe it's, always going to be something like 4 times r. Now, I don't think it should be purely based on the circle, because imagine if we drew x out here, and talked about the perimeter, or if we had the same circle and we had x really close, you'd definitely be getting different perimeters. So it doesn't just depend on r, it also depends a little bit on x. And it's this sort of, mental examination of, gee, what if I moved x around here? What would that do? What if I, shortened the radius? Could that affect things? Well, yeah, that would affect the perimeter. So we start to realize what things do have an effect on the perimeter. And certainly the radius of this circle and the position of x are involved. Maybe things like this angle. Maybe things like length xy. I guess it might be time to add in t and see what we can imagine. So I'll just put t here, I guess. So it doesn't really matter, and we shouldn't be placing t on our diagram anywhere particularly special. Don't try and fool yourself into placing t directly on OX. You might get a false sense of the problem. We'll put V here, we'll put W here. And, So once I have t, that gets me v, and that gets me w. Now, I got this. It's the blue perimeter that I want. And maybe I can relate it to some constant, or maybe I should put t right on this dividing line and then compare it to all the other possible t's. I don't know. So v and w are on there. Now, as I highlight this, I notice there are sections vy and wz, which catch my attention from my previous analysis of xy and and xz are the same length. And, well, y is still a tangent point even with respect to v, and t is the other tangent point. So with v connecting its tangent lines up to the circle, you get y and t, and so these have to be the same length. And the same thing happens with w, because t is the tangent point there. So these guys are going to be the same. And so it's the two blue lines plus one green line and one red line. And so, yeah, I think we can get the perimeter of this triangle as a constant. Let's just sort of talk it through. So I might start, because we have to write this up. So I might say something like, regardless of my choice of t, we notice vy and vt are tangent to the circle. Similarly, wz and wt are tangent. To the circle. Alright, so that's a fine observation. Now, if you're going to use a circle geometry result, and circle geometry pops up every now and again on the Euclid, it might be useful to, remind them of what you're talking about. So I might say, if I have a point P and a circle here, I would say something like the tangent lines from P to the circle are identical. We'll use the yellow. Okay, if you think someone might not know the result you're talking about, write it down. And I'll say something like, since they are tangents from the same point. By the way, if you didn't know this property, that might be something to look up, is Google like circle geometry, circle properties, that sort of thing. But if I pick a point and a circle and I connect up the tangents, you will get the same lengths. And we did just talk about how to prove that. Since they are tangents from the same point, they are equal. So we'll flip the page, and that means that Vy equals Vt. Therefore, Vy equals Vt, and Wz equals Wt. Okay. Now, the perimeter of xvw is xv plus xw plus vw, but xv plus xw plus vw is xv plus xw plus, I'm going to split up the vw because t lies on that line. Not necessarily in the middle, but t lies on that line. Okay, so I split those up, but now I can use my circle geometry fact, xv plus xw plus vt is the same as vy. And tw is the same as wz. And now what I'm going to do is I'm going to group these together. xw plus wz. But these are, of course, xy plus xz, which is independent of our choice of t. And we could even go a little stronger and say it's 2xy or 2xz, because they are the same length, but that's really, I think, irrelevant at this point. We have written the perimeter that we wanted to talk about, which looked like it depended on t, because v and w both depend on t, but we rewrote it as an expression that doesn't depend on t. Okay? So I think that's enough for A, and we talked about our circle geometry results. We had a couple pictures, so we have certainly done enough work, I would say, to get full marks on A part. Now there is a B part, which we should expect to be a little longer. And what have we got here? So B part, in the diagram, AB is equal to 10. Okay, they're actually giving us lengths here. BC is 14. And AC is 16. Odd choice of numbers. I'm not seeing anything. They're not Pythagorean triples or anything like that. They are all multiples of 2. M is the midpoint of BC, so I guess these are both 7. Various lines can be drawn through M, cutting AB. So here we have an example PQ. We could also, have this line here, this line here. Tons of lines we could have going through M. So various lines can be drawn through M, and we cut AB. The point on AB is called P, and the point on AC would be called Q. Okay. Determine with proof the minimum possible perimeter of APQ. Okay, so we want the minimum possible perimeter there, and at least unlike the last question, we'll have because we're given actual lengths, we should get an actual numerical answer of, maybe 22 or something. I don't know. So we want length here. Okay. We want minimum possible perimeter of APQ. Interesting. So we have a possible perimeter, because we know AB is 10, BC is 16, and AC is AC is 16, BC is 14. So we have a possible perimeter of 40. I suspect we can probably get lower. The question is how? Isn't that always the question? Now, in the last question they talked about perimeter, and in this question we're talking about perimeter. Does that mean the two are related? Not necessarily. In more recent Euclids, you would expect your A, B, your C to all be related. But with older Euclids, this year, 2007, sort of the gray area when people were transitioning the types of questions away from, just a really hard, solid question to how quickly can you grapple with a brand new concept. That's what more recent Euclids are like. 2007 was sort of transition, but if you go back to things like 2001, 2003, you can get A and B parts for, 8, 9, 10 that don't really have anything to do with each other. Like, you don't use the proof in A anywhere in B. It's just, they're both geometry questions, or, they're both logarithm questions. And you can still sort of get that today on questions sort of 7, 8, and 9, but question 10 is usually all one brand new concept nowadays. So the question is, are these two, do we have 10A and 10B because, they're both geometry themed and they're both asking about perimeter? Or, as we investigate B, is our answer in A going to come into it at all? And I'm not entirely convinced that it is. I don't see an obvious way to add a circle in to sort of our diagram in B part here. It's still, it might, because we're talking about possible things going through M, and I guess up in A we were talking about possible values for T, but that came out with a fixed perimeter, and alright, well, if I were going to use A, I would need a circle. And I would need a circle, and we'd have to have a choice of some point T, I guess. Because we have the right setup in that we have a point, in this case A, in A part it was X, and we got two rays going out from it. And in the first question, we also had a circle, and we picked a point T. In B part, I guess the closest analogy would be we have a point M, and now my question is, should I draw some sort of circle with M? Or is there some clever way to show, here's M, and then if we have this circle, we get this tangent, and somehow that's the smallest possible perimeter? I don't know if that's going to work, because A part doesn't talk about small perimeters. But if I don't have to, if I'm not using A part, what could I be doing on B part? That's the real question. There's lots of different PQ values. We could draw a couple. Now, just as experimentation, we always have the same A, B, C, and M. It's just, we have lots of different PQs. And there comes a point, I think, like a P down here wouldn't work, because we'd start to, I guess, it would go through here. You'd have a Q down here, and I don't really think that would work out. So there's going to be a limit to the PQs, to the values of Q. Because you don't want one down here like this. But we can have, a P up here. And there are lots of different values. I'm just not seeing what would be the best way to get a perimeter, because as soon as I fix my P, obviously I'm going to get a Q. And I guess we're given BC, as I've said, ABC is some fixed value. And so what we could do is say, okay, suppose P is X units away from B, Q is then going to be Y units away. And can we figure out PQ? Well, I think we can figure out the angle at A, so we could probably do some trig stuff there. I'll give it a little bit of a try, but then maybe we'll have to go back and look at the circles. Let's see. So if I had X here, and I had M here, so there's 7, there's 7, and I want to figure out Y. Y will be in terms of X. These angles are going to be the same. What is the angle at A? I know we've got 10, 16, and 14. So, I'm hoping this is a useful angle. Cos A, I'm just going to use the cosine law to get A. It'll be... opposite. No, it's the two side ones squared. I don't have to often rework the cosine law backwards in my head. The two opposite ones minus the one that you've got. The two non-opposites minus the opposite divided by 2 times the non-opposite ones. So that'll be 100 plus 256 minus 196 divided by 3200. The 6's at least will cancel out. 250 minus 190 is 60. So we get 160 over 320. Oh, this is nice. This is 1/2. Cosine of 1/2, so therefore A is 60. We're probably going to have to use that. That's a nice angle to work with. And then what could we say? We could say PQ is going to be... What if instead of calling that x, I might call this the angle in here theta? We can do things in terms of theta, right? Maybe. That would have to be theta as well. So the perimeter of APQ would be AP plus PQ plus QA, which I think, depending on our choice of theta, we can work out. And also, I just realized why A is 60 degrees, because this is a 5, 7, 8 triangle in disguise. It just multiplied the sides by 2. Anyway, so this is the expression we need to minimize. I know I've got 60 degrees here. I wonder if maybe just having it be equilateral would minimize things, but I can't guarantee that. Now, what could we do? So AP is going to be 10 plus X, whatever it is. And then there's going to be PQ, which I can figure out by cosine law once I know X and Y. And AQ is going to be 16 minus Y. Okay. So what can we do here? This is starting to seem like it's going to be a really annoying trig problem. And I have to believe 10b has a cleaner solution. So maybe we'll try and add in a circle. But, I mean, this is looking slightly promising. Let's just take a look. I'm pretty sure these angles here are not nice. Oops, sorry, this angle down here. I don't think these are nice numbers to work with. I like the 60, but I think the rest of them aren't good. How do I need to use them? I need to get X, and so that's sort of a sine law. I mean, it clearly can be done. The question is, should we waste time doing it? And if you've gotten to question 10 or question 9, you likely are running out of time, unless you're, one of those super geniuses, in which case, why are you watching my channel? And so the question is always, should I try and do this? Should I try and do this? It can be done. I think it's going to be messy. I'll give it a try. If nothing else, this might serve as a what not to do question. We'll stumble on the real solution later, but it certainly can be done this way. And then we'll get everything in terms of theta, and then, something like theta is 45 might minimize it. 45 degrees, of course. Okay. So once I know the angle up here at B, that's theta plus this angle. The angle up here at P. And then that angle at P, sine of that over 7 is the same as sine of theta over X. So we'll redraw the picture, and we will just focus on that top part. So there's M. There's P up there. Okay, and P is based on our choice of theta. Theta being measured from BC, I guess. So there's B, and we want X. We've got 7 here. There's P up there. So I'll call the angle at P alpha. So alpha plus theta is the angle at... Actually, we'll call them the angle at P, just to be consistent. So the angle at P plus theta is equal to the angle at B. X over sine theta is equal to 7 over sine angle at P. It might be that some of this stuff just sort of cancels out. We also have a 7 down here. We have another theta. And we have the angle at Q. Oops, sorry. Q is down here. This is C. So the angle at Q here is theta plus the angle at C. And it's the sine values are the same, so call this y. Y over sine angle at Q is still the same, or y over sine at theta, sorry, is equal to 7 over sine angle at Q, because sine is the same whether or not it's the angle or its supplement. Yeah, supplement is the one that adds up to 180. So these are all nice and true. Now I know angle P and angle Q add up to 120. That's fine. So this is turning out to be really hard. All this stuff is going to be set up, but now I'm thinking, okay, the only way I can think to get sine at B, or to talk about the angle at B, would be to use the sine law, because I know we got sine 60 down here. So, sine 60 degrees over 14 is the same as sine angle at B over 16, which is the same as sine angle at C over 10. And that's fine. It's going to get me sine angle B and sine angle C, but then I'm going to have to use the sort of sine of alpha plus beta laws, and that's just going to be a mess. So I'm going to stick a pin in this. I might have to come back to this, but I believe there's got to be a simpler way. Now, trigonometry was just my first idea. I guess we can try and add a circle in here. So I've got my A, I've got my B, I've got my C, I got M as the midpoint, and that's about it. I'm not going to draw the line BC here yet. Actually, no, let's add that in. So now, if I were going to use part A, I need a circle. And so that's the question is, where could the circle go? The circle needs to relate to the diagram in some meaningful way. Can I force the circle to be tangent at both B and C at the same time? I don't think so. I'm fairly certain. Actually, no, you can't, because then B and C would be the tangent points, and these would have to be equal, because A is a common point. It's the intersection point of both tangents. So I can't make my circle hit both B and C at the same time, and so I don't think I should make a choice that, it should be tangent at B or tangent at C. Okay, so let's pick a different location for our circle. I think I can pick it so that it can be tangent to this line. And then we'd have, say T is our tangent point here. But we're not, in the question, we're talking about lines that pass through M, not lines that pass through T. So while we can make a circle do this, I don't see why I would want my circle to do this. And I'm fairly certain M is the midpoint of BC, but M is not going to be happen to be the tangent point if the circle is tangent to BC. So I guess the only other possibility would be our circle passes through M. But does that help me? I can certainly do this. I can certainly pick a point, and it's going to have tangents, and we might call this, y up here, and this z. And so M is a point on the minor arc z, and so I guess we can still talk about lines passing through M, and maybe it's the tangent to the circle that passes through M that we care the most about? That sort of seems to be the only available setup. Now, I like that that tangent line is special, and I could believe that tangent line gives me the minimum, but why? So let's explore this option for a moment. We can draw a circle tangent to AB and AC that passes through M. Should I justify that? Well, it's a well-known circle of Apollonius problem. But more than that, I would say it's pretty clear we can do it. Just sort of, I would say just get a circle that's tangent. You know, we can pretty quickly draw a circle that's tangent, just sort of move them further out. And eventually, as we, sort of hit all the continuum of circles as they get bigger, eventually one of them will pass through M. So you could also explain it that way. Circle of Apollonius, these are great problems in terms of constructing circles that are tangent to certain things and pass through certain points. Either explanation is fine. That, or we can draw a circle, just start making them bigger. So we can draw a circle tangent to AB and AC that passes through M. This is not a problem. So now it's got to be, if we're going to use A, it's got to be the tangent line that passes through M that gives me my smallest perimeter. It's got to be. That's really the only unique value we could have. And so if that's the case, then I've got two things to do. I have to figure out what that perimeter would be, and I also have to show it's the smallest perimeter. So we'll draw a slightly bigger picture. So we've got a circle. And we'll call the tangents Y and Z. I don't think I said that on the last slide. Call tangent points Y and Z. Fine. So we got M here. And I don't quite know exactly what this is going to do. I'm fairly certain M is not the midpoint of its tangent line. So we've got sort of A and B is out here, and okay, so we've got M, and it sort of looks like this. It's not exact. There's sevens here. Whatever. Now pick a PQ, a line PQ, I guess. Going through M. If it's not the tangent, that's the tangent has to give us the minimum. Otherwise, we could probably use some sort of mirror argument. Because the tangent is a very special line. So we'll give these guys, we won't call this P and Q, we'll call this R and S. So pick another one. Maybe a P is down here and Q is here. And we'll complete the circle a bit more. That is just an awful looking circle, but the point is it's part of our picture. If PQ is not tangent, so what makes it not tangent? Well, then it would pass through the circle twice rather than once. So if PQ is not tangent to the circle, it will pass through another point other than M. Let's call that point N. So on our picture, N is up here. Okay, so now the question is, how can I show that this is bigger? That's the real trick, is what can we do? So A is down here. So it's the fact that we have this extra point N, I guess, that matters. Or at least I hope that that's... Whoa! At least I hope that that's what matters. So there's P. I probably shouldn't draw my pictures so close to the top, should I? So there's P and Q. I can't for the life of me figure out what exactly I would do. Well, let's mess around a little bit. I know if RS is my nice tangent line, then I get a parameter of AY plus AZ. We worked that out in the last question in part A, and that would be using part A. So can I show that APQ in this case is more? So, we've got this little extra bit here, but we also come back a fair bit here. Let's just color code the heck out of this. Now, those two green lengths are supposed to be the same. I know they don't look it. These two purple lengths here are supposed to be the same. I know they don't look it. And then... Actually, these two blue lengths aren't the same, so let's pick a different blue. There we go. What to do? So the reason I'm not giving up on this yet is because I gave up on the trigonometry one because it looked like it was going to be too hard to calculate. I haven't given up on this one yet because I haven't exhausted the list of possible ideas. I feel like there's some way to show that this PQ has a bigger perimeter. I'm just not seeing it for whatever reason through my diagram. And maybe redrawing it will help me out a little bit. Let's just focus on... I really should draw my circle first, frankly. But I keep forgetting to. So whatever, there's M. I'm going to stop drawing BC. I don't think I need that right now. I think I will need BC and all its wonderful values for calculation purposes later. I mean, we do know that we've got 60 degrees here. I don't think we need it yet. Oh, incidentally, when I have Y here and I have Z here, because we have the same length, it's isosceles, so if I just quickly draw between those two, I'm going to have 60 degrees and 60 degrees. So they're all going to be the same length, and that will probably help us somehow to calculate something later. But that's just planning in the future. That 60 degrees is quite nice. Okay, so here's our tangent one. It's the good one. And then we've got, pesky PQ. And maybe focusing on that point N that must exist is throwing me off. Maybe that's what I need to stop worrying about. We'll call this R and S again. So now the question is, how do I show that APQ is bigger than ARS? That's the challenge, that's the trick. Well, I think I'm going to show, okay, I can add in this point N. What I want to do is I want to show that PQ is greater than PY plus QZ. Because with RS, we know that RY plus, we know that RS is equal to RY plus SZ. Because we've got, this value is equal to this value, and these two values are equal to those two values. So I want to show this. So now at least I have a plan of attack. The question is, can I pull this off? Can I figure out a way to do this? I suppose we could use the power of a point theorem. So power of a point says if I have a certain, it doesn't have to be outside, but ours are going to be outside. If I have a point here, call it, I don't know, D. And for our purposes, we'll need sort of these other points. So if it cuts through at EF and then, it's tangent at G, turns out DG squared is, and regardless of what chord EF we've got, DG squared is the same as DE times DF. So this is power of a point, if you want to look it up. Cross ratio is what we've got here as well. Actually, no. I think power of a point is just when it's the tangent line. Anyway, it doesn't really matter. But the point is, from this, I can see that QZ squared is the same as QM times QN. And PY squared is the same as PN times PM. Now, QM and PM, that's nice and relevant. QN and PN. So we've got sort of values A, B, C, and D. A plus D is the same as B plus C. So I feel like there's something I can do here. So I have to write this up because it's a written solution, so we'll write it on the other side just because I've run out of room, but I think power of a point will help us. So referring back to our diagram, by power of a point, some people abbreviate this as POP. Most people in the marking room will recognize that. We've got QZ squared is equal to QM times QN, because, there is a point N. We already commented on this already, and it would need to be part of our write-up. PY squared is PM times PN, but QN and PN add up to, so this is QM times PN, or sorry, PQ minus PN. and this is PQ minus QM times PN. So if I add these, let's expand them out. So 1 becomes QZ squared is equal to QM times PQ minus PN times QM. PY squared is equal to PQ times PN minus PN times QM. If I bring these guys together, so that's still 1, that's still 2. Let's add these together. So PY squared, I'm going to bring these guys over to the other side, plus 2PN QM plus QZ squared is equal to QM plus PN all times PQ. I don't know. I think this started out with good intentions, but I'm not seeing a way to show what I want to show. I want to show PQ is bigger than something. And that is yet to be what I'm able to do. Okay. So I like the QM plus PN. I like that there's QM and PN here. It makes me think QM plus PN squared. That's certainly something that my eyes are drawn to. Can we make it work at all? Well, what if instead up here we did... No, I was gonna say we rewrite it all in terms of M or something like that, but I'm not entirely convinced that that's going to help. In fact, I can't write it all in terms of M because I got this pesky QM sitting around. So we'll make it go back to the way it was. So QM plus PN. Now this is less than PQ in its entirety because M and N split the two. So I know for a fact that this is less than or equal to PQ squared. Because we've got Q, M, N, and P. So QM and P, that adds up to less than the total QP, unless M and N are at the same point. That's why I have a less than or equal sign. So now the question is this enough? I'm not sure this... What is it that I'm trying to show? I feel like I've gotten stuck, I've gotten lost, and that's usually a time to stop and rewrite some things. So I want PQ is greater than PY plus QZ. This here is obviously positive, so I could definitely say that PY squared plus QZ squared is less than or equal to PQ squared. I don't think that's enough. Alright, that just shows that I can't have a Pythagorean triangle. It doesn't show that py plus qz is less than pq. So we're going to have to go back to the drawing board if this is going to work out. And this might not work out. This might have all been for nothing. And maybe the trigonometry way is the way to go, or maybe there's another geometric thing that I'm not seeing. I liked this power of a point, though. I liked it. It didn't seem to like me. Can I rework this at all? QM plus PM adds up to PQ. Same with PQN and PN. Could I do QM PQ minus PN and just leave it as PM times PN? No, because when I add that up, the PNs are going to have opposite sign. This is a positive PN. This one up here is a negative PN. So I've got A times B and I've got R minus A, R minus B. That's essentially what I'm looking at. R is equal to PQ. And I want to show that these square roots here are less than R itself. So what would we naturally do? Well, we'd naturally square them. So I'd want AB plus 2 and then all this stuff. Plus R minus A, R minus B. I'd want that to be less than R squared. So if I can guarantee that, I can get this. So that's QZ squared, that's PY squared, and that's PQ squared. And what is this nonsense in here? 2 square root QM PM QN PN. And that's what I can't seem to get. So maybe it's not power of a point I need. I don't know. It seems once again that it's just too sort of calculation intensive. And it also seems kind of inelegant for a geometry question. I'm going to go back to the picture. Maybe just power of a point isn't the way to go. This time I'm going to remember, draw the circle first. I should always draw my circles first. That's sort of a lumpy potato, but that's pretty good, I guess. Okay. I wonder how many more times I'm going to have to draw this picture. Alright, so we've got our circle, and we've got M, and we've got what I'm calling R and S. And those, it's got to be that is our simplest answer. Okay. So from those guys, we have these tangent points Y and Z here. And that determines our perimeter for ARS. And if we had another line PQ that wasn't tangent, that would force the existence of some n, sure. But we want to show that APQ has a bigger perimeter than ARS. Now, I thought we could just compare it to AY and AZ. Power of a point was the first thing that popped into my mind. That didn't seem to go well. Working out these tiny little areas, changes in lengths, hasn't seemed to do it. So I want to show. So let's continue writing this up as I think. Let RS be line through M tangent to the circle. And we're saying let PQ be another line. What do we want? We want perimeter of ARS to be greater than, sorry, not greater than, less than or equal to perimeter of APQ. And so from this, I decided to turn perimeter of ARS into AY plus AZ and tried to compare it that way. So what else could we do? I don't think we can calculate this perimeter any other way. But maybe we're not using part A hard enough. Maybe we need to calculate the perimeter of APQ in a similar fashion. But what would that entail? We can draw, I'll use the other red, we can draw yet another circle whose tangent to our new line PQ at, say, T. So we can definitely do that. That's a line sort of thing. Basically, just, once again, you could say it's Apollonius 3. This is an X circle of PQA, or it's a line Apollonius problem, or just start with a small circle that's tangent and shift it that way. It's going to get bigger. Eventually, it will just be tangent to the line. So this is certainly possible. And then that's going to be tangent at two other points. What haven't we used? T. So might call them U and V. And we'd want to show that U and V are strictly further away from A than Y and Z. Would that work? To find... so this is equal to AU plus AV, where U and V are tangent points to the circle that is tangent to AB, AC, and PQ. And this circle can definitely be found, again, if we want to, just write a little side note as to why this works. So we would need to argue that U and V are further away from A than Y and Z. So that's what we need to do. So, is that even possible? Well, the picture seems to make me believe it's true. But does it actually work? So, once again, this is 2AU, and once again, this is 2AY. Because once again, if we have a circle and we have these two tangent points coming from the same given external point, you get the same length. So that's fine. We just need to make a little bit of an explanation. So all we need to do is show that u must be further away than y. Well, let's suppose the opposite. So the perimeter of APQ is equal to 2AU, which is greater than or equal to 2AY, which is equal to perimeter of ARS, if and only if U is further from A than Y is. Okay, so let's suppose the opposite. Suppose U is closer to A than Y. So what do we have in terms of a pic? We'll flip the page again. So what would that look like? I forgot to draw my circle first again. Alright, so there's Z, there's Y, and we were using the red, I guess. So let's say it's U here. And it'll be the same distance forward. So U, V. So PQ will go through here. And that's our T here. P and Q is here. And then what would we have? Well, it seems kind of obvious from the picture that if this were the case, PQ wouldn't intersect our line here. So there's S and R and our tangent point M here. But so this is tricky. What can we say? I might not even have the pictures drawn properly. In fact, I can't have the pictures drawn properly. Because PQ shouldn't be able to pass through M at this point. Not only that, there should be an M and an N that it passes through. And yet I'm not seeing that on my picture. Now maybe I've drawn my picture improperly, and that can certainly happen. So we might want to strive for a better picture, but just trying to think through the picture and see can I think of a way to draw this so this would be satisfied. And if I can't, how do I put that into verbal words? I don't think this can happen. Like, obviously this can't happen. That's what we're trying to argue. And me saying that doesn't really help. But maybe a proof by contradiction isn't the way to go. So what did we have? We had a picture, a more recent, more accurate picture a little while ago. It's got to be that there exists this N here. So how did we get this T, this point of tangency? it has to be further over, which is not a mathematical term, but how can I express that? So these circles... U is found by making the circle tangent to PQ. Which intersects our original circle at M and also another point N. The new tangent point T doesn't exactly lie between M and N. Well, no, it does lie between M and N, doesn't it? Yeah. So I guess, in a sense, the new circle center has shifted further from A, and this places U and V further from A. There might be a more technical or exact, because this is kind of a verbal explanation, but there might be a more exact way to do this. But, I mean, that's definitely what the picture is doing, and I think the picture combined with the words is enough to get my point across. If we'd done this the trigonometry way, which I admit would have been a headache, probably would have been more exact. But, you know, it's a geometric argument. We got pictures, we got words. I'd say that's fine. So then U is further from A than Y. So therefore AU is greater than AY. So the perimeter of APQ is greater than the perimeter of ARS. Fine, I think that's finally done. So we get the minimum perimeter when we have RS which is tangent to the circle passing through M at M. Alright. But we're not done there. And that's why I'm okay with sort of the more vague verbal explanation I gave, because we're not even done the problem yet. We still need to figure out the perimeter. That is what they asked us to do, right? Determine with proof the minimum possible perimeter. So now I know that I'm shooting for the tangent point. I still have to work out what this perimeter is. But at least I have now proven, I guess, that it's going to be at that tangent point. So let's draw another picture, and let's try and remember to draw our circle first so our diagram doesn't look terrible. Okay, so there's M, and now we need to bring back BC. So there's M, we get this 7 here. We are also probably concerned with Y and Z up here. All I need to do is figure out AY, and we're all set. And let's add in RS. Now we already know that we've got 60 degrees. Got 10 here, and we've got 16 overall here. And I want to figure out AY. So let's figure out, we get point O here. And now, what are we to do? Well, let's get purple. We'll connect O up to our points of tangency here. Let R be the radius of the circle. So we get R here, we get R here. Might as well add, here goes R here, and M is a tangent point, so it doesn't look like it, but we do have a 90 degree here. Splits it in, does it split it in half? Yeah, I think it does. No, it can't. It doesn't split it in half. Doesn't split RS in half. Okay. What else can we do? We could connect O and A up together. It doesn't necessarily go through M, so we're gonna have to draw it kind of carefully. I'll draw it with a little bulge so it goes around M, so it's a little more clear. If I were writing this up nice and super neat, I would probably try and put M off to the side somewhere and make it more obvious that he doesn't pass through. You know what? We can even extend that a little further back, and maybe now we can use power of a point. I'm going to call this point D and this E, and we still have some more R's there. So, what is there that we can do? That's the challenge now, is figure out... I feel like if... So AO splits this into 30 degrees here. 30 degrees, 30 degrees. And we have a 90, so these are going to be 60s. I don't think we need M anymore. We might in a moment, but I don't think we need it exactly. So we're gonna leave that out for just a second. But we have R, some distance, R, an R here. This is gonna have to be 2R. So this guy's also gonna have to be R. And AY. So we have a 30, 60, 90 triangle, 30 degrees. A 90 at Y, O here, A here. And we know the shorter length, the length opposite the 30 degrees is R. So I might say by 30, 60, 90 triangle, AO is 2R, AY is going to be root 3R. You could also do this with some more trigonometry. But we got this point D on here, and DO is R. So AD is R. Well, we got root 3R. So as long as I can figure out R, I'm all set. And the perimeter is 2AY, which is 2 root 3R. So now I just need to figure out the radius of this circle. That's our brand new challenge here. I don't think A passes through M, as I've said a couple times now. But I don't have any actual length to work with right now. So I've got to relate it back to AB or AC, or more likely BC and M and that sort of stuff. So we'll draw the picture once again. But now the challenge is just, can I get the radius of this circle? So there's M. We've got 7, we've got 7, we've got 10. I can figure out AM just fine. Well, not just fine, but I can figure out AM probably. But I need to relate this to R somehow. So we've got D here. And that's a distance of R there. We get 30 degrees up here. We have some angle between these two. And not a whole lot else is falling into place in terms of being helpful. But there's got to be some sort of setup here. That's what we're looking for. Is there something else we can do with the 60 degrees? I can't relate the 30 and the 10 and the 7. That's the problem. Because the 30 doesn't necessarily match up with... The 30 degrees doesn't go to M. That's the trick. So what can we do? Do I need to be focusing so heavily on M? Could I use B and C in some meaningful way? Because I don't just have M. I do have these 7s, and I've got to add I've got to use them, because I don't think the 10 or the 16 off to the side are going to be especially helpful. And I don't even have a radius really on this picture other than D. So if I put a radius here, now here's Z. I do have a radius I can connect up to Z. I can extend a line to C, but I don't know if that would be especially helpful. I suppose I can put Y up here. And I know AY is root 3R, which is what I'm trying to find. And I come back a distance 10 here, so I guess this would be root 3R minus 10. And, you know, I know AC is 16, and AZ is root 3R, so CZ is going to be AZ is root 3R. AC is 16, so CZ is root 3R minus 16, or is it... The picture makes me believe that it's 16 minus root 3R. That's what's got me confused, but, yeah. One of them's... Surely one of them has to be further than... Are they necessarily further than the points of tangents here? Is my picture just sort of throwing me off? I feel like another diagram. How many diagrams have I drawn? Somebody count it and leave it in the comments. Alright, let's see if we can get a very nice, very clean circle. That's pretty good. I used a stray pop can that I have. And even that was not a particularly good circle. Okay, so we got that. Bah! This question is trying my patience, even just when it comes to diagram drawing. See, that's a much better circle, and that wasn't even with a Coke can. Alright, so there's... Alright, we'll draw BC first, so that our point of tangent C at least looks like a middle. And I guess Z's down here, so yeah, maybe I can have... But it really didn't look like it in that other picture. So we got 10, we got 16, I guess this is root 3r minus 10. This little bit in here is root 3r minus 16. I'm probably sweating the small stuff when I shouldn't really care, because I imagine I'll probably get some sort of quadratic if I keep going like this, and it won't really matter if C and Z are swapped. So what can I do? Get this O here. Still add in R. Fine. Suppose I can add these lines in. That gets me a couple right angle triangles, and I do have this R here and this R here. So I can get OB and OC in terms of R. Does that help me, though? Then do I want to connect OM and get an R there? And then I've got these two 7s. And even if I do that... Yeah, because there is a right angle there, but it's not when I meet BC. Well, let's at least calculate OB and OC. It can't hurt to have more of these. Or more information. So OB squared is R squared plus 3R squared minus 20 root 3R plus 100. And OC squared is... Yeah, this really doesn't seem like it's helping. R squared plus 3R squared minus 32 root 3R plus 256. So technically, I guess we've got 4R squared minus 20 root 3R. And then I guess, could we do... Maybe I've got OB squared and OC squared. Could I use, what am I thinking? Cosine law, maybe. I don't know. We'll think about it. So we'd get 4R squared minus 20 root 3R plus 100. And OC squared is 4R squared minus 32 root 3R plus 256. And then it's opposite of 14. But I don't have an angle that I necessarily know. I do know I've got 60 down here. But I don't know this angle, I don't know this angle, or this angle. Now I know YZ technically would get me a 60 degrees, and I guess I haven't used connecting up YZ as a thing yet. But I don't quite know what I would need to do there. This is turning out to be a really lengthy question. I wonder if the trig might have been a better way to go. So, I'm just trying to think, how can I use this OB squared and OC squared? I definitely don't want to square root them, and I don't recognize them as squares of anything in particular, so I don't really have OB and OC to use. And I know OM is R, but again, I'm not really seeing that as helpful. Unless, well, maybe if we do add up the r there, and then I've got this angle here is, let's say, alpha. This is going to be 180 degrees minus alpha. And cosine of supplementary angles, you negative them. So I think I can relate OB squared in terms of 7 squared and r. Yeah, I think I've got it. Okay, so by cosine law, OB squared is BM squared plus MO squared minus 2BM MO cos, we'll just say angle BMO. And OC squared is CM squared plus MO squared minus 2 CMMO cos angle CMO. But of course this BMO plus CMO equals 180 degrees. So we can change this into angle BMO, and I think we'll be able to cancel them out. So this is, yeah, so they'll, because this is 7 squared plus r squared minus 2 7r cos, call it alpha, I don't know. And this guy here, I don't know why I drew the line so early. But this is 7 squared plus r squared plus 2 times 7r cos alpha. So if I add these two, OB squared plus OC squared is going to be 49 plus r squared plus 49 plus r squared. And these parts are going to cancel out. Okay. And now I know OB squared and I know OC squared. It was 4r squared minus 20 root 3r plus 100 plus 4r squared minus 32 root 3r plus 256. And that's equal to 2 49s is 98 plus 2r squared. So we have 8r squared minus 52 root 3r plus 356. I smell a quadratic. 98 plus 2r squared. So I'll bring the r's over to the other side. 6r squared minus 52 root 3r plus, I don't know how to do that off the top of my head. So 356 minus 98 is 258. And that should be equal to 0. And now we'll get r. And from there we can get root 3r. In fact, if I let s equal root 3r, I have 2s squared minus 52s plus 258 is equal to 0. Divide by 2 on both sides. I will get s squared minus 26s plus whatever 258 divided by 2 is. 129. And this is, I want twice this length, so we want 2s. Actually, I suppose I could have multiplied everything by... Yeah, instead let's do that. I'm going to let p be the perimeter. So I'm going to let p equal 2 root 3r, because that's the value we want. So I'll get 12r squared minus 104 root 3r plus 516 is equal to 0. So I multiplied everything by 2 so that now I can say this is p squared minus 52p plus 516 is equal to 0. Now I just need to solve for the value of p and we're done. So p is equal to negative b plus or minus square root. I'm not even going to bother to see if I can factor that because the numbers are just weird. 52 squared minus 4, a is 1, And C is, I think it was 516. Let's just quickly go back and check that. Yep, 516. All over 2a, so that'll be 2, so we can divide that by 2, get 26 here. Divide everything in here by 4, so that'll make it 26 squared. So we're looking at 26 plus or minus square root of 26 squared, which is 676, minus 516. That's doable. All over 2. Although now I'm a little suspicious because we're going to get both values, two values for p that can work. But we'll do... Oh, and we don't need over 2. We got rid of the over 2. But the 516 can turn into... So the 16 and the 76 there, so it'll be 660 minus 500. So it'll be plus or minus square root of 160. Which I'm sure we can cancel something out. I can bring out a factor of 16. 26 plus or minus 4 root 10. And root 10 is about 3 something or other. But one of these values shouldn't work, and I'm just a little confused as to which. 26 minus 4 root 10. Surely, I would think the smaller one is what we want to go for. Let's see. What would the bigger one be? Because we know, for example, that we have, 10, 14, and 16. We know 40 is a possible parameter. Maybe we can go smaller than that. But 4 root 10, I'm just going to grab my calculator. 4 times square root of 10, 12.6 plus 26 is 38.64. So that is smaller, so I can't rule that one out. But now the question is, which one of these two works? I made an assumption, didn't I, that we had 16, we had root 3 r minus 16, didn't we? I made that assumption. That had to be an actual length to work with. Now, can I make, so 26 minus 4 times root 10, so that's 13.35. I divide that by 2, divide that by 2, I'll get root 3r, and that is 6.6, which is bigger. So I will say something to the effect of, we need root 3r to be greater than 16 and greater than 10. So 26 minus 4 root 10 is too small. So it's got to be the plus version. (26) plus 4 root 10 is the perimeter. It's about 38. That's really close to our 40. It makes sense that our perimeters would be so similar. Is the minimum perimeter. Ooh, boy. Okay, that was a long question. Like, a really long question. I was unhappy basically the whole way through that. I tried trigonometry, it seemed too complex. Tried power of a point, that did not get me anywhere near the minimum. I had to use a verbal argument I wasn't happy about. I'm also not happy with my verbal argument as to why the 13.3 as the perimeter wouldn't work. I mean, I think it all works out, but I don't think I was as elegant as I could be. And so if you're looking for a really elegant solution, I imagine their solution is probably at least much better with the explanation, but I'm fairly certain we've got the right answer at long last. But wow, that took a lot out of me. And it's a shame, because I found the rest of the paper to be fairly nicely flowing. But question 10 was a brick wall. All right, but that's the 2007 Euclid for you. Some of you out there probably did better on question 10 than me. Some of you might have done a little worse, and maybe you learned a technique or two. As always, you can click the second link in the description. You can go to get all the past contests put out by the University of Waterloo, and you can see their solutions. And, oftentimes their solutions differ from mine. So take a look at their 10. Maybe they had a much faster, much more obvious way to do this. I would be curious to see if somebody actually managed to go through the trigonometric way that I was starting to do. I think it's too calculation intensive, but if you're someone who really likes your double angle formulas, really good with trig, I would love to see it if somebody wants to write that up. I think that'd be nifty. I might even try and do that once I turn off the video. But there we go. The next Euclid will be the 2008 Euclid that I have planned. 2008 papers in general are coming up, but if you want other Euclids that I already know I have posted, 2006, 2005, these are all nice recent papers, so feel free to take a look at those. If you're looking for something a little lighter, but still written, try the Hypatia questions. Hypatia 2007's up, and just try other Hypatia contests in general. But no matter what you do, I will see you for more math in the next video. Take care.